If I were building a geospatial system from scratch today, then you would find me building a data lake. And no, that's not because I'm from Minnesota, but there are 4 reasons why data lakes are going to change geospatial forever. So at its core, a data lake is just a collection of files. This could be any file from an image, a music file, or a data file. In the case of geospatial, that could be things like GeoJSON, of course, but data lakes are best used with cloud-optimized geotiffs, GeoParquet, and what's known as PM tiles. We'll get into what all of those are in a minute. But what's really nice about a data lake is when you need to add new data, all you're doing is adding a new file to a file system. You don't have to change anything or move it to a new database or go through any tricky ETL. You just drop it in there. Now that's the beauty of the data lake. And of course you want to be organized, and things like partitions are particularly useful for this. More on that later. And using file-based table formats like Iceberg and Havasu are also really important, but more on that later too. The key here to a data lake is that all your data is in one central cloud storage location like Amazon S3, Google Cloud Storage, or Azure Blob Storage. I don't know why whenever I hear the name Blob Storage, I think of Slimer from Ghostbusters. I'm not sure why. Now, the data lake lives in what's known as cloud storage, and cloud storage is known in the cloud ecosystem as a cloud primitive. This means that it is one of the fundamental building blocks for all other aspects and operations in the cloud. These other cloud primitives include things like databases and compute services. Now, without storage, you really couldn't do anything else in the cloud. You need a place to put your data, and that cloud storage is the place to do. And as data scales have increased over time, cloud providers have been incentivized to keep their costs low and keep it as a very scalable service, considering so many things are built on the back of it. Now, we talked about some of the big services from Google, AWS, and Azure, but if you use one of those cloud providers, you're pretty much set to go. But if you don't, there's some other reasonable options as well. Some of those other options include DigitalOcean, the sponsor of today's video, Cloudflare, and Backblaze, which all provide very cost-effective solutions for large amounts of data, as well as very generous or free egress. So what egress is, that means if you were to read your data, which is one of the most common operations that a data lake can perform, you can get those reads at no charge, which is pretty important when you're building your data lake. A quick special thanks to our sponsor for this video, DigitalOcean. In addition to many other services, DigitalOcean provides highly scalable object storage that it's S3 compatible and includes a built-in content delivery network with over 200 distributed servers around the globe. For just $5 a month, you can get 250 gigs of storage and a terabyte of outbound transfer. If you need to go beyond that, the service scales up at very low cost options. Go ahead and click this link to get started to use DigitalOcean storage services as well as the other services within their ecosystem. So we've established that data lakes are extremely scalable and cost effective, and they work with any geospatial data you might need. Since in blob storage, you can put literally anything you want in there. This can work with any geospatial data that you have. Now, of course, as I mentioned earlier, this will work best with your cloud native spatial file types. This includes things like GeoParquet, cloud optimized geotiffs, and map tiles created using PM tile. Now, PM tiles is particularly interesting since map tiling as a service can be quite expensive, but as you can see here, simply creating and hosting them on the cloud storage, your data lake can be very effective for storing this visual layer. So now we can actually host data, we can host raster imagery, and we can host web tiles all in one single data lake. This is all contained, scalable, and cost-effective, like we said. So now we've collected all our data in one place. Let's look at this as a giant collection of Lego. We have different files that we can pull into this one location, and as we need to store more, well, we certainly can. As you can see, we have different shapes and sizes of things here, but this is getting pretty unorganized. That's one point we're going to address next. You want to make sure that your data lake isn't just a giant junk drawer of data. So look, there's two things that you can do here. One thing that you need to do is appropriately name your files, and you can also keep them in an organized structure, which is basically like folders, but much more organized. The naming strategy is up to you, but a common way to do that is naming their files based off of their date or when they are loaded into the data lake itself. For example, you can take a look at this file, which has one single name and a date stamp and the hour it was created in. This can also allow you to look across multiple files with the same name and update the file query with the date ranges at the end. If I'm looking for a specific date range, I can effectively use that file name just as a query parameter itself. Now, Parquet files, and by extension GeoParquet, have their own special system for doing this called partition. Partitioning is basically a way of splitting up a set of data into more manageable pieces. Let's imagine that we have a data set of 1 billion points scattered across the United States. One way we could partition that is by date. We could look at the date value on that and partition it by year or month or any other date metric or range that we want to. Another way to do this is we could use partitioning by state name. We could include the state names or some other attribute in our data. Effectively, any data column or attribute that you have in your data, you can use as a partition. Now you want to do this strategically, and you don't want these partitions to be too granular. These partitions and the names associated with them can act as filters for your data in your query. The great part is here that the query will only look at that range of data or the partitions that you've provided. And if you limit out everything else, your query is going to run much faster downstream. Now you might be wondering why you want to spend all this time meticulously organizing and uploading your data to one central location if you can't get into the tools you actually use. And now comes the reason why you spend all the time doing this and creating this wonderfully organized data lake. Having the central data lake makes it effective and easy to pull all this data into the tools you already use the most. On the screen here, you can see all the different tools that support reading remote files and that also have geospatial capabilities. In short, the data lake can effectively act as a data storage layer, but also the query layer for all these different tools at one single time. One data lake, multiple tools. Doesn't matter how many of them you use, all the data in the data lake remains the same. So let's dive into a few of these tools so we can see just how they're used and what you can do with them. First, we're going to start with DuckDB. DuckDB is probably the easiest to start with because it integrates and can read files directly from your data lake. As you can see here, you just have to enter the credentials for your data lake or your data storage system, and then you can read those files in. Now you can query them just like any other table. Your table name is effectively your file path in your data lake. Now what's really great is it works natively with GeoParquet. So this is a simple and easy setup to go ahead and get started with. PostGIS also allows you a few different options to use a data lake. If you want to do this directly from Postgres and PostGIS, you can use the Parquet foreign data wrapper and connect that to a remote data lake. Of course, you can also use DuckDB and the DuckDB foreign data wrapper if this is the route you want to go, all within inside PostGIS. And finally, if you just want to create these files and move them directly in as tables, you can do that too and create these native tables within PostGIS. Just managing the ETL workflow and keeping them up to date is the only thing you need to do. Plus, one of the coolest things here is that PostGIS also supports remote raster table reads from cloud storage. You don't have to actually pull the data in. You can just keep it where it is and read it from there. And finally comes Apache Sedona with its cloud counterpart Whereabouts, which provides spatial capabilities on top of Apache Spark, which is an extremely popular system for data scientists to prepare large amounts of data for machine learning, but also for data engineers to create data pipelines on large volumes of data. Not only does Apache Sedona and Whereabouts support the reading of GeoParquet datasets, but they're also very efficient at creating them and pushing those datasets back into your data lake. On top of that, Apache Sedona supports the reading of raster data, and Whereabouts also allows you to integrate remote raster data. This includes things like spatiotemporal asset catalogs or stat catalogs, and they can directly import those as remote datasets. This means you keep those raster files in your data lake and you only read them when you need to for specific operations. They stay there and they just are connected in as remote file connect. Like I said, there's many other file systems you can do this with. You can read files directly into Python and things like GeoPandas and others. Long story short, the integration and applications are quite endless when you pull these datasets into your data lake. Now, if we go back to our giant bucket of Legos, it probably looks something more like this. We have it a little bit more organized and everything looks nice and clean, so we can go on our merry way, right? Well, here's one of the tricky parts about a data lake. I mentioned that cloud storage is one of those cloud primitives, and it doesn't keep a record of the changes that you make. If you remove something or update it, it just kind of happens. There's no record of that taking place. Going back to our Legos here, if I was to delete this file represented by this Lego, once it's removed, it's gone forever, and I don't know that it happened. Same thing with updating. If I take this Lego here and put it over here, I'd also have no record of that change taking place. Now, the good news is that there are solutions for this, and there is a toolkit called Apache Sedona or Delta Lake. Both of these solutions are fairly similar with some minor differences. If you really want to get into those details, I would check out this video here. But one of the first things it does is allows you to create tables directly out of your files. You can write common SQL against them, and it looks just like a table, but it's a table represented within the Iceberg or Delta Lake ecosystem. This also means you can perform CRUD operations such as create, read, update, or delete operations against those tables. You have to remember that these are represented as files in your data lake, so you're not actually creating a database, but Iceberg and Delta Lake provide that layer on top of it, basically helps it act like a normal database would. Finally, these systems allow you to do time travel and understand how tables were changed and updated over time. It keeps that historical record for you, and there's a few extra things like some extra partitioning capabilities that allow you to make the reading of your data much more effective. So going back to my Lego example, I now have a history of all these changes that I've done. I can see this data table went away and I moved this data table over here. Plus I get a little bit of extra organization on all of the organization I already did. So the one big gap right now is that neither of those systems supports spatial data natively. You would either have to turn your geometry data into well-known text or well-known binary, and then translate that into a geometry within your query, which adds time to the work you're doing and is certainly not. Whereabouts actually took a stab at solving this problem by creating a version of Iceberg called Havasu that supports spatial data natively with all the great features of Apache Iceberg that I just mentioned. This works really great for both vector and raster data, specifically remote data. For example, imagine that you have Overture Maps data and you want to connect that back in as an out-of-database table. You can just leave it in that remote bucket and call it when you need it. Same thing happens with raster data stored in files or spatiotemporal asset catalogs. Let's imagine that this data is stored in AWS Open Data and I just want to read it in for when I need it. I can simply reference those parts that I need, and when I'm running my query, I can leave it in that location and we'll call it in and I need it. There's no extra cost to me to store my data, and you get your own basically chain of data lakes. So long story short, I think data lakes are great. I hit 3 of the reasons why I think that is, but there's one little thing that you need to address, and that was the 4th point, which I don't have time to talk about in this video. Now imagine you spend all this time creating this amazing data infrastructure. You need to make sure that people actually use it. Now, in some cases that might mean they query the data directly, but in many other cases, people just want to be able to get the insights they need when they want them at any time. So go ahead and check out this video where I talk about the specific thing that is holding back most geospatial practitioners and how you can fix it using tools like this.